right? Remember that not means standard state. So my free energy change in its standard state for my reaction does occur under standard state conditions. So this is for standard state conditions. And then just remember standard state conditions, solids, liquids, and gases are in their pure form. If it's a solution, it's a 1 molar solution. So my concentration would be 1 mole per liter. If it's a gas, it would be 1 atmosphere of pressure, and then 25 degrees Celsius for my temperature, which is 298 Kelvin. What we're going to do in this section is we're actually going to relate free energy changes to equilibrium constants. And at standard state, delta G naught actually relates to K. It's used to predict reactant or products favored at equilibrium. So delta G naught, this relates to K, K being my equilibrium constant, right? We spent chapters on this, Kc, Ka, Kp, Ksp, Kw, right? If I have a capital K, it's my equilibrium constant. So this relates to the equilibrium constant. It predicts whether reactants or products are favored at equilibrium. If it's not in its standard state, delta G, without the naught, it actually relates to Q. And I've mentioned Q a couple times in this chapter. Remember, we defined Q in the same way that we defined K, except that the concentrations that we plug into the expression aren't necessarily equilibrium concentrations, right? So concentration of products over reactants raised to a power equal to the coefficient, excluding pure liquids and solids. It's just that we're not plugging in what we know are equilibrium concentrations. It could be any old concentration. So this is actually relating to Q instead of K, and it predicts spontaneity. We can use delta G naught to predict spontaneity too. It's just that often it tells us which direction we're going to get to equilibrium. Remember, equilibrium is our goal here. So predicts spontaneity. The big one though, right? Delta G naught is relating to equilibrium constant, delta G is relating to Q. So an equation for us, delta G, so I'm not at standard state conditions here, is going to be equal to delta G naught, so my standard state conditions, plus R is my gas constant, T my temperature, multiplied by the natural log of my equilibrium or my reaction quotient. Q is my reaction quotient. So just, I know I'm kind of repeating myself here, but delta G naught, this tells us the direction of the spontaneous reaction. When both the reactants, I'm just using an R, and products P are in their standard state conditions. I had said above that it was used to determine right, whether it's going to be reactants or products that are favored at equilibrium. And it's like, it's both of these things, right? It's going to determine whether it's a product or a reactant favored at equilibrium, but it also tells us the direction that it's spontaneous. Like, it's still a delta G, but it's negative, it still tells us the spontaneous direction. We can just tell, because we're going to relate it to K later, whether it's reactant or product favored. So I'm going to just add that second part again. Is it By it, I mean the reaction. So is the reaction reactant or product favored? At EQ. And we'll come back to this, which is why I'm repeating it so much now. Delta G is when it's not a standard state. We're going to use that to determine spontaneity, whether the reaction is moving forward or reverse to reach equilibrium. And then, will the reaction proceed forward or reverse to reach equilibrium? Right, determines spontaneity. Remember, things want to get to equilibrium. So is it going spontaneous in the forward direction, or if it's non-spontaneous, it would go in the reverse direction to reach equilibrium. So let's do an example using this problem, or using this equation. So we're going to calculate the free energy change at 25 degrees Celsius for the following reaction. So I'm going to have nitrogen, which is a gas, and we're reacting it with 3 hydrogen gases, and I'm producing 2 ammonia, also in their gas state. I know that my pressure of nitrogen is 0.010 atmospheres. My pressure for hydrogen is 0.030 atmospheres, and my pressure for ammonia is 2.0 atmospheres. We're given our standard free energy change. If you weren't given this, you could calculate it. It's using delta G naught F, right, from your Gibbs free energy of formation, right? We have a reaction, so we can get our sum of our products and subtract the sum of the reactants from it. So I'm giving it to you this time, but it is very possible that you would have to calculate it. Kilojoules per mole. I'm going to rewrite our equation down here just because I scrolled out of it, and I mentioned what R and everything was, but I want to actually write it down. So I have delta G is equal to delta G naught plus RT times the natural log of Q. So my gas constant, and there are 2 values for the gas constant. There's one where the units are liters atmospheres per mole Kelvin, and that's the one you would have used in your gas law chapter in 150, 151. There's also another one where the units are joules per mole Kelvin. That's the one that we want to use. So because we're solving for energy changes, we want to use the gas constant where the units are in terms of energy. Remember, joules are our unit for energy. So 3.14 joules per mole Kelvin. And this number is on the back of your periodic table. You don't need to memorize it. You just need to make sure that you use the correct gas constant. I'm just grabbing the periodic table right now to confirm what I'm saying. Yeah, this one, just like you had in 150, 151, it has both of them on there. So just make sure you use the correct one. Since we're solving for energy, we want to use the one that has units of energy. So there's 2 R's on the back of your table. Make sure you use the correct version of your gas constant. Q is our reaction quotient. which I've totally forgot how to spell, reaction quotient. Remember, this is our concentration of products over our concentration of reactants, and then we're raising them to powers equal to our coefficient, right? We set it up just like we set up, I'm just raising it to m and n for now. Like you set up your equilibrium constant, it's just, they don't necessarily have to be equilibrium concentrations. Do remember we're given pressures in this problem that we could solve for equilibrium constants and our reaction quotient using partial pressures instead if everything was a gas. So that's what we're going to do. Instead of using molar concentrations, we'll use partial pressures in this problem. So it's actually going to be the pressure, right? The pressures of my products over reactants raised to a power equal to their coefficient. So, or in terms of pressures, partial pressures. So that's how we're going to do it in this problem. Our temperature was given to us as 25 degrees Celsius, right? T is temperature. It does need to be in Kelvin. That's pretty standard. And then I think we have everything to actually do the problem. You can do it all in one step, or you can solve for Q first. I usually like to solve for Q first. If I try to do everything in one step, I tend to make mistakes. So I'm just going to set up Q and do that first. So I have 2 NH3s, so I'm going to take 2.0 atmospheres, and I'm going to raise it to the second power because there's 2 moles of ammonia. And then on the bottom, I have 1 mole of nitrogen, 3 moles of hydrogen. So my value for nitrogen gets raised to the first power. And then my value for hydrogen gets raised to the third power. I'm writing down the units. I'm just going to end up ignoring them when I'm done because just like with equilibrium constants for Q, we don't have to include those units. So I'm going to take 2, raise it to the second power, so 4, and then divide it by all my stuff on the bottom. And I get a really big number. So 1.5 times 10 to the 7th power. And again, you can do that work as part of the whole thing. I don't know, I function better when I break stuff into pieces. So I have that number. I'm now going to plug everything in. So delta G is going to be equal to delta G naught, which was given to me as a negative 33.0 kilojoules. We are going to have a unit issue. My gas constant is joules per mole Kelvin versus kilojoules. So we are going to have to do a unit conversion. And I'm doing this pretty lousy. This is not proper scientific notation. Never, ever, 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 ever write your answer this way. But this is part of my work and not my answer, so I'm okay with this. If you want to do this as part of your work, that's fine. Just don't ever write this as your answer because this is not how you would do it. But I know that there's 1,000 joules in a kilojoule, right? 10 to the third, so I'm just slapping 10 to the third at the end of it. So you can move your decimal place over, which is essentially what I'm doing. So just, again, don't ever write an answer like that though. Remember, whenever you're writing scientific notation, you have to have 1 digit and then the decimal point. So 33 would become 3.3, so that gets smaller by a factor of 10. So then 10 to the third needs to get bigger by a factor of 10. So this would be the proper way to write it. I'm fully aware that this is wrong. But again, it's part of my work, so I'm just gonna leave it that way. If you want to make like the same sort of like shortcuts, that's fine. Just don't ever write an answer that way, please. That's not how we do it. That actually, what I just scribbled out was correct. That I'm leaving isn't how you would write that number. I'm just being lazy. So then I'm gonna add to that 8.314, I gotta start writing smaller here, joules per mole Kelvin, multiplied by 298 Kelvin, and then that's multiplied, we're going to go sideways here, by the natural log of 1.5 times 10 to the 7th. So that's my value for Q, and you do need to take the natural log of that number, not log base 10. Be careful, we've been in log base 10 for a pretty long time. I'm just working this out on my calculator right now. And I get that my free energy change comes out to be, and we'll round for sig figs here in a minute, I get a positive 7,938, and then that's in joules per mole. I do only want the 3 significant digits in my answer. Actually, I just want 2 significant digits in my answer. I have 2 over here, sorry, 1.5. I didn't see that because it's going up the side in a really non-professional manner. It's also joules per mole in a pretty big number, so I'm actually, as I round it, I'm going to convert it to kilojoules also. So I'm going to write 7.9 kilojoules per mole. So I'm just moving that decimal place over 3. So spontaneous or non-spontaneous? Yeah, non-spontaneous. And that's in the forward direction. It's always in the forward direction. So if it comes out positive, it's non-spontaneous in the forward direction, which means it's going to be spontaneous in the reverse direction. So it's going to need to go in the reverse direction to reach equilibrium. Right, non-spontaneous in forward direction. Right, when we set up our reaction quotient, right, Q, we did products over reactants, and we made these the products. So because we did it that way, this answer is in the forward direction, right? Products are our products. So it would be spontaneous in the reverse. Things spontaneously go towards equilibrium, so we could say needs to go in the reverse direction. To reach equilibrium. Right, we said that our free energy change, if I go back up here, will it proceed in the forward or reverse direction to reach equilibrium? It's going to go in the reverse direction because it is non-spontaneous in the forward direction. So as a reaction proceeds towards equilibrium, whatever direction that may be, so as a reaction proceeds towards equilibrium, and then we're going to write some things under there. So our first one is if we have too much reactants. Right? Remember our reaction quotient, Q, I'm just going to write it up here, is going to be products over reactants. So either concentration if we're solving it in terms of molarity, or pressures if we're solving it in terms of partial pressures, but it's still going to be products on top, reactants on the bottom. So if we have too much reactants, I know that Q is going to be too small, right? Because my number on the bottom is much larger than it needs to be. So Q is going to be much less than 1. So what that means, RT times the natural log of Q, I'm just taking this from our equation, is going to be also less than 0, right? The natural log of 1 is 0. So this is actually going to be less than 0 because Q is less than 1. That makes sense, right? This is going to be a large negative number mathematically. So then if we look at our equation, delta G is equal to delta G naught plus RT natural log of Q. This part is a large negative number. So when I add that to my delta G naught, I'm actually going to end up with a negative delta G. So what that means, the forward direction is spontaneous. Right? It's a positive value, so spontaneous. Spontaneous in the forward direction, the normal direction, right? Which means to get to equilibrium, we're going to decrease my reactants and increase products. So products increase while reactants decrease, right? It's just going spontaneous in the forward direction. So too much reactants, I'm decreasing my reactants and increasing my product. Delta G comes out to be negative. The opposite then, if I have too much product, so again, just going back up to how we're setting it up, right? My number on the top is going to be too large. So if I have too much product, Q is going to be much larger than 1. So RT times the natural log of Q is going to be much greater than 0, right? It's going to be a large positive number. So back to our equation, right? Delta G is equal to delta G naught plus RT natural log of Q. This is a large positive. So when I add that to my free energy change that's at standard state, delta G comes out to be positive. So what that means for us, the forward direction is non-spontaneous, so the reverse direction is spontaneous. Right? It's going to decrease products and increase reactants. Trying to be consistent here as to how I'm writing it. So my reactants are going to increase while my products decrease. So what happens if we're at equilibrium? So at equilibrium, my free energy change is going to be equal to 0, because remember that's what happens when we're at equilibrium, and Q is actually going to be equal to K, right? I am plugging in equilibrium numbers, so it is my equilibrium constant. So if we take our equation, delta G is equal to delta G naught plus RT times the natural log of Q, and then substitute those values into it. I have 0 is equal to delta G naught plus RT times the natural log of K, right? Q becomes K if I am at equilibrium. I am going to rearrange to solve for delta G. So delta G naught is going to equal to negative RT times the natural log of K. So we had said kind of at the beginning of this section that delta G, my non-standard state, relates to Q. Delta G naught, right, at standard state, it relates to K. So this is that equation. And it could be any version of K, Ka, Kb, Ksp, Kw, any of those. So if delta G naught, right, is less than 0, spontaneous, right? And what that means, if that's a negative value, then the natural log of K needs to be a positive value, right? Because there's a negative in the formula, so a negative times a positive would give me a negative value, right? Delta G needs to be negative. So my natural log of K is greater than 0. For that to be true, K has to be greater than 1, right? My products need to be greater than my reactants for that to be true, right? K, just like with Q, is products over reactants. So if I want that number to be bigger than 1, the number on top needs to be larger than that on the bottom. So it's mostly products at equilibrium. Right? When we started this video, I had said that delta G tells us is it mostly reactants or products at equilibrium. This is how we're relating it to that. If delta G naught is greater than 0, right, it's a positive value, we know it's non-spontaneous in the forward direction, of course. For that to be a positive value, I do have that negative in my formula again, right? This negative. For this part to come out positive, this part has to be negative, right? I need a negative multiplied by a negative for it to come out to be a positive value. So I know that the natural log of K is less than 0, right? It's a negative value. So I know that K has to be less than 1, which means my number on the bottom is larger than my number on the top. So it's mostly reactants. And then if it is at 0, right, then my natural log of K is equal to 0, so K is equal to 1, right? The natural log of 1 is equal to 0. So it's an appreciable amount of both at equilibrium. So another example for us using this new equation. We want to know what is the value of the equilibrium constant so we're solving for K for the following reaction. At 298 Kelvin, question mark. So I have carbon monoxide, which is a gas. We're adding to that 2 hydrogen gases, and I'm getting CH3OH, which is methanol, and at this temperature it's also going to be a gas. And we're given delta G naught in this problem. Again, it could be a problem where I don't actually give you that value and you have to solve for that value. So you could do that a couple different ways depending on how I design the problem, but we could use delta G, right, F. So we could use our Gibbs free energy of formation. We could use those values. We did a problem like that. You could also use, if I wanted to be a real jerk, we could use this formula, and then we have to solve for those using, right, delta, right, my heats of formation and my standard molar entropies. So there's different ways we can get that number that we've solved in this problem, or that we've solved in this chapter. For now, I'm just going to give it to us, but I could have a question where you have to come up with that on your own first and then do the problem. So we could do this just given this question, this reaction, and appendix G. I wouldn't actually have to give us that value. Our equation, delta G naught is equal to negative RT times the natural log of K. K is what we're solving for in this problem. That equation is on the back of your periodic table, as is your gas constant, but again, make sure you take the correct value. We're solving for energy, so we want the one that's in terms of energy. The units on that are joules per mole Kelvin. The free energy change that I gave us is kilojoules, so we do need to convert, and I'm going to do that crazy. Don't ever write your answer this way, because I'm just going to mark it wrong way, but it's my work. So I'm going to take that value, and then I'm going to throw 10 to the third after it, because that's how many joules are in a kilojoule. Again, don't ever write your answer that way. If you think you're gonna get into a bad habit doing it as part of your work, then don't do it as part of your work. Actually write it correctly. So 2.51 times 10 to the 4th would be the correct way to write that. So my gas constant multiplied by my temperature multiplied by the natural log of my unknown, right? We're solving for K. So I'm going to do all of the work except for the last step. So I'm going to multiply my gas constant times my temperature, right? I'm going to multiply those together. I'm going to take that whole thing, the negative of it, don't forget the negative in the formula, and divide it through on both sides to get rid of it, and then I'll have a number equal to the natural log of K. So, and then we'll do the last step. So I end up that the natural log of K is equal to 10.1. And then the reason I wanted to do this is we haven't used natural logs in a while. We did in chapter 12, which was the first chapter we did this semester, but I don't know that we have since, unless I'm forgetting something. But we need to take the anti-natural log, so that's where we have to use E. So my equilibrium constant is going to be equal to E raised to the 10.1. On your calculator, it's probably the second function of your natural log key. And I'm going to write the whole thing, and then we'll talk about rounding and sig figs and all that stuff. So 24343. I don't have to put units because I'm solving for an equilibrium constant, so I don't need to do that, which is good because log values don't have units. And when we used chapter 12, we did kinetics and we used natural logs. I hadn't given you the rule for log values yet, but you now know it. So because 10.1 is a log value, only that 0.1 counts. So I actually only want 2 significant digits in my answer. So one significant digit in my answer. It's 2 is what I'm going to write down. So I jumped the gun on you, but it's going to be 2 times 10 to the 4th.